1012 Cassandra nodes. Zero downtime. No maintenance window. That's not a press release number, that's an operational constraint that most distributed systems teams would treat as a reason to schedule a weekend war room and pre-write the incident postmortem. Yelp didn't do that. Here's what they actually did, why it matters, and what you can steal from it if you're managing anything stateful at scale. First, some context on why this is worth your attention, and not just an InfoQ summary of a blog post. Cassandra upgrades are genuinely hard in a way that, say, upgrading a stateless API fleet is not. When your nodes hold data, you can't just roll a new AMI, drain, replace, and call it done. You have to think about gossip protocol compatibility, compaction behavior across mixed versions, token ring stability, and the fact that a node mid-upgrade is simultaneously a reader and writer in a replication group that has real traffic hitting it. The blast radius of getting this wrong isn't a 500 error on one endpoint. It's potential data inconsistency across a distributed store that your application may not surface until much later. That's the operational reality. So when a team does this at 4-digit node scale without dropping requests, it's worth understanding the mechanics. Yelp's Cassandra footprint is not small. Over 1,000 nodes spread across what they describe as multiple clusters serving production workloads. The InfoQ piece is a summary of Yelp's own engineering blog post, so let's be clear. Most of the concrete detail comes from Yelp's own write-up, and InfoQ is largely paraphrasing it. That's fine, but go read the source if you want the full picture. What the summary does give us is enough to reconstruct the approach. The core strategy was a rolling upgrade with strict rack and data center awareness. Nothing surprising there in principle. Cassandra's replication topology is designed to tolerate this, but the execution details are where teams usually get burned. Yelp used a node-by-node rolling process where each node was drained, upgraded, and validated before the next one started. The key word is validated. They didn't just check that the node rejoined the ring. They verified replication factor consistency, checked that read and write latencies returned to baseline, and confirmed that the gossip state stabilized before moving forward. That validation gate is the thing most teams skip when they're under pressure to finish the upgrade window, and it's exactly where silent data issues get introduced. They also stage the upgrade across clusters rather than doing all clusters simultaneously. This is obvious in retrospect but worth stating explicitly. If you have cluster A and cluster B both serving production, upgrading them in parallel doubles your blast radius for no benefit. Yelp serialized across clusters, which means the total calendar time was longer, but the operational risk at any given moment was bounded to one cluster's worth of nodes. Now, the version question. The InfoQ piece is unclear about which specific Cassandra versions were involved, what they were running before and what they upgraded to. That matters because the upgrade path from, say, 3.11 to 4.0 involves a gossip protocol change and a new storage engine format for some table types, which is a fundamentally different risk profile than a 4.0 to 4.1 point release. If you're planning a similar exercise, you need to know your specific version delta, because the compatibility matrix is not uniform. I'd recommend checking the Apache Cassandra upgrade documentation directly for your version pair, rather than assuming Yelp's path maps to yours. What they do describe clearly is their use of automation tooling to manage the upgrade sequence. They built internal tooling, unclear from the reporting whether this is open-sourced or proprietary, that handled the sequencing, the pre-flight checks per node, and the rollback triggers. The rollback trigger piece is important. They defined explicit criteria for when to stop and revert a node rather than leaving that decision to human judgment in the moment. That's good operational practice, because at 1 in the morning when a node is behaving weirdly, the last thing you want is a judgment call about whether the metrics are bad enough to roll back. You want a threshold that was agreed on in daylight by people who weren't stressed. The traffic handling during the upgrade is worth examining. Cassandra's consistency level configuration is doing a lot of work here. If you're running quorum reads and writes with a replication factor of 3, you can tolerate one node being unavailable per token range without dropping requests. Yelp's zero downtime claim is valid under that model. They weren't actually serving requests from the node being upgraded, they were relying on the remaining replicas to cover it. This is not a trick. This is Cassandra working as designed. But it does mean that zero downtime is contingent on your replication factor and consistency level being configured correctly before you start. If you're running local quorum with ref2 somewhere in your cluster because someone made a cost optimization 3 years ago, that's where your downtime lives. One thing the piece touches on but doesn't fully quantify is the timeline. Over 1,000 nodes rolling one at a time with validation gates between each one. That is weeks of calendar time, not a weekend. Yelp doesn't publish the exact duration from the info queue summary, but you can back-of-envelope it. If each node takes 15 minutes to drain, upgrade, restart, and validate, and you're doing them sequentially, 1,000 nodes is roughly 250 hours of upgrade time, not counting the intercluster serialization gaps. In practice, you'd parallelize across nodes that don't share token ranges, which compresses that significantly. But the point is this is a long-running operational process, not an event. Your team needs to be comfortable running something like this as a background operation over weeks, rather than a heroic all-hands weekend. The monitoring setup they describe is worth noting. They were watching replication lag, compaction queue depth, and read and write latency percentiles, specifically P99, not just averages at each step. If you're doing something similar and you're only watching average latency, stop. Averages hide tail latency spikes that are exactly what you'd expect when a node is mid-upgrade, and its neighbors are temporarily handling extra load. P99 and P999 are the numbers that will tell you whether your users are actually experiencing degradation. What can you actually take from this if you're managing a stateful cluster, Cassandra or otherwise? A few concrete things. First, define your rollback criteria in writing before you start, with specific metric thresholds, not vibes. Second, validate each node's replication state before moving to the next one. Automate that check so it's not skippable under pressure. Third, know your consistency level and replication factor configuration across every key space before you touch a node, because that's what your zero downtime claim actually rests on. Fourth, serialize across clusters even if it takes longer. The time cost is real, but the risk reduction is worth it. And fifth, if you don't have tooling that can sequence and gate a rolling upgrade automatically, build or adopt it before you start. Doing this by hand across 1,000 nodes with a runbook and a spreadsheet is how you introduce human error at 3 in the morning on day 12. The underlying story here is that Cassandra's operational model actually works if you use it correctly. Yelp didn't do anything exotic. They used the replication and consistency mechanisms the system was built around, added automation and validation gates, and exercised patience on the timeline. That's not a novel technique. It's disciplined execution of known practices at a scale that most teams find intimidating. The real takeaway is that the intimidating part is the scale, not the technique, and scale is just a reason to automate the validation, not a reason to skip it.